Hi, and welcome to the last module, Module 9 of Lecture 5. Here we're going to put it all together. Now, we've gone through a bunch of different rules here. We had rules for how to integrate three different types of function, powers of x, exponential functions, and logarithms. And then we went through three different ways of dealing with more complicated integrals. 1, the integral is a linear operator. 2, integration by substitution, and 3, integration by parts. I tried in the course of these modules to indicate how each one followed either directly or more or less directly from the analogous rule in differentiation, to show that these are not just disconnected random rules. They actually come from a single place. In fact, in some senses, all the stuff we've done in the last two lectures have come from a single definition of a derivative. Right? Once you have the derivative definition, we derived all the rules for the differentiation from that. And once we try to find the inverse operator, we derived all the rules, pretty much all the rules of integral calculus from that, from the associated rules of differentiation. Not all, but most. Right? Other than perhaps the fundamental theorem of calculus. Okay. Now, it might be handy, however, to have the rules put all in one place. So again, the textbook, page 149 of this printing, has all the rules right here listed for you in section 7.4 if you wanted to go back quickly and see them. Now, when presented with an integral, right, and there's 3 steps you really should start. First, well, 4 steps, I guess. First, try to see if it's just a really simple integral, that it's the simple application of one of the rules for powers of x or exponential function or a logarithm, right? If you have that, you're done. Second, try to see if it's some kind of combination, some kind of sum or difference of simple functions, right? So for instance, if you have something like this as a polynomial, this is a sum and difference of powers of x with constants in front of one of the things. So you can use the fact that the integral is linear to integrate that sum. So really quickly, you can just do the integral of that. You pull down, you raise it to the power x to the third, divide by 3, you get 2/3 x third. You divide this one by 4, and you divide this one by 5. And there you go, you've integrated this polynomial. That's the first step. If you can't apply the linear rule to the derivative, to the integral, to the integrand rather, next look to see if you have some kind of composite function involved there. Examples we've talked about are things like e to the x squared, or the natural log of x cubed minus 1, or even something like 2x minus 1 to the 1/2, the square root of 2x minus 1. In all these cases, you have a composite function. Here, e to the x is composed with x squared. Here, log of x is composed with x cubed minus 1. And here, the square root of x, x to 1/2, is composed with 2x minus 1. So in all these cases, you have a composite function. When you have a composite function in your integral, what you should naturally think of first is, can I use substitution? Substitution is a very delicate one, and it only works, as we saw in the previous module, when the derivative of the argument of the outer function, right? So x squared, the derivative of x squared, the derivative of x cubed minus 1, or the derivative of 2x minus 1, those are all the inner functions. Whenever the derivative of that inner function multiplies the outer function. So to use this one, I would need some multiple of x out front. To use this substitution here, I'd need some multiple of x squared out front. And to use it here, I can use it always because I just need some multiple of 1. So that tells me when I can use substitution. can use substitution only when I happen to have the derivative of the inner function multiplying the outer function. That, as you might guess, is a relatively rare scenario. So substitution can't be used that often, but when it can be used, it works really nicely and greatly simplifies your integral, as we saw in the examples in the previous module. Okay. If you can't do substitution, as you will often not be able to do, that leaves integration by parts. That's more of a brute force method. You can't always tell if it's going to work or not. What you look for first is whether or not you can identify two functions that are multiplied together, call one f and one g prime, and then see if the f can be made simpler and the g prime not too much more complicated. If you can do that, then you can apply integration by parts, as we saw in the previous module, to integrate products of functions. Or quotients, in that, for that matter, since a quotient is just, since 1 over x plus 1 squared is just x plus 1 to the negative 2, which is a product, which you can treat as a product. For instance, this equals this, which is just a product of two things. If you can identify an f and a g prime that have those properties, then integration by parts has some chance of working, or at least is more likely to work. Sometimes you may have to use it more than once. If your f gets simpler but not simpler enough, that's often true when f is some power of x, and the more you differentiate it, the simpler and simpler it gets. You won't, again, always know if integration by parts are going to work ahead of time. Sometimes it does, sometimes it doesn't. As we say, it works more often when f can be made simpler through differentiation, and g prime does not get too much more complicated through integration. If that doesn't work, though, it is not necessarily the case that you just can't do it. It's entirely possible that it can't be done with these techniques at all, or maybe it can't be done at all, right? So for instance, we talked about these earlier in the class, right? This integral we can do, and did a variant of this one. This integral we cannot do, and I mentioned the x's, we cannot do using any technique in this class. However, it can be done. The definite version of this integral cannot be done analytically. There's no way of writing that in a nice closed form. You have to use numerical approximations. In the first case, you can do it yourself. In the second case, you can look it up. So if you Google or any other search engine you want, list of integrals, you'll find many, many websites that list tons of integrals. You can find the integral. You can try to convert your integral into one you see there using substitution, changing the variables, or some other technique. Convert your problem to one you see on the list of integrals, and then apply the list to help you out. In the case of a numerical approximation, there exist tables for the important ones, for which you can look up the value on that table of something reasonably close to your problem. Or you can find a computer program, many of them exist, you'll use many of them in the course of doing statistics, and plug in your problem and potentially get out the answer, particularly when it involves distributions and areas under the curve for those distributions. In other words, when it involves definite integrals of common distributions, you can often get those answers via common statistical programs such as R. That's it. So just to recap, derivatives, you can go through, break them up, simplify them. You eventually would get them to a smallest piece that you can differentiate, and then you're done. You just build it back up again to get the big derivative. Integrals, not quite so much. You can do quite complicated ones. We've done already quite complicated ones just in the course of this lecture, using these relatively simple rules, relatively few rules at least. But there will be cases where you just can't do it at all. And there, the best bet is to go look up a table of integrals, online or in a book, and try to make your integral into that one. Or if you can't find one of those, go online. There are free programs that integrate things for you. One is called Maxima. You can download it, install it, and integrate some of the things yourself as long as it's not too complicated. If it is too complicated, try to simplify your integral to a form such that they have on the list or a form that's accessible to the program. And that's it. Thank you for watching this lecture, and the next lecture we're going to give the payoff to a lot of the stuff we do in calculus, finding extrema of functions. Thank you very much.